Hi, good afternoon, and welcome to today's lunchtime lecture. I'm Paul McMillan. I'm Professor in Chemistry, and I'm a member of the Lunchtime Lecture Committee, and it's my pleasure today to be the host. So today we have Dr. Carina Fearnley from the UCL Hazard Centre, and she's going to be speaking about communicating lethal risks. This is an initial slide just to show that these lectures are being sent out, being streamed worldwide through the internet, and there is the possibility to send questions in from anyone either in the room or else externally, either using the Twitter feed or else through the Slido account. And so we welcome you to do this. And as we go through the questioning after the lecture, we will take questions from people external to the room. And so with this, could I please ask you to make sure that your phones are switched off so that we don't disturb the speaker? And welcome to Carina, and thank you.
Thank you. Good afternoon, everyone. I'm delighted to be here. So as Professor Paul has already said, I started off at the Hazard Centre, and I now work in the Department of Science and Technology Studies. And this talk is really going to, in a way, show that journey from becoming a scientist to actually questioning what's going on. So we're going to have a bit of shaking, a bit of rattling, and a bit of rolling, and that's basically me saying that we're going to be talking about earthquakes, volcanoes, and tsunamis. So hopefully you won't feel too seasick by the end of the hour. Now, what happened with me was that this event happened in 2004, the very famous tragic event of the Boxing Day tsunami that hit primarily Indonesia and Sumatra. And you can see here's a photo of these people being taken by surprise about the tsunami that's happening. And this was one of the most deadliest natural hazard disasters in living memory and recorded memory. Over 225,000 people died from this event, and over 1.7 million people were displaced by it. And it affected over 11 different countries. And what I found quite interesting is, as you'll see from this schematic from NOAA in America, you can see here how the tsunami was created in Indonesia and how it then spread across the whole of the Indian Ocean and eventually pretty much throughout the whole world. And the question really was, for me, as someone who'd studied geology at an undergraduate level, my question was, why did so many people die when we can detect earthquakes and we can make a good guess that a tsunami has been generated and communicate those? So what happened here? Now, it's interesting because you'll see from this diagram that many, many hours later, the waves are still going around. But what's interesting is if I bring up a chronology of events, you can see that, okay, those people who were living very near to the earthquake that generated the tsunami had very little time notice. But those in Thailand and beyond had 2 or 3 hours. So again, what happened? And the problem was that there was no early warning system in place at all. There was nothing to communicate the information to the various people who were taken by surprise, effectively. They had no idea what was going on. Now, tsunami detection in itself is quite a complicated and expensive process, and it requires quite a lot of infrastructure and goodwill and finance to keep it going. But of course, you also need to have a system to communicate that warning. And one of the dilemmas was that the Pacific Tsunami Warning Center had picked up the earthquake, thought there might have been a tsunami, and wanted to pass that information on, but they didn't have the communication network to do that. So what is an early warning system then? And this seems a very simple question, but actually it's a very difficult question to answer. And in fact, one of the best definitions I can find is that by the United Nations, which it says here is the provision of timely and effective information through identifying institutions that allow individuals exposed to take action and to avoid their risk and reduce their risk. That's the general gist of it. So as part of that, what we want to do is, if we're thinking about natural hazards, that are pretty lethal risks, what we want to do is be able to know what's going on. And that means we might want to, in the case of earthquakes, have seismometers that are going to measure seismicity so that we can detect that earthquake. Once we've then got the monitoring equipment there to pick it up, we then want to communicate that over and process it and make sure that it's accurate. We then have to make sure that people actually receive that message, whether it's by SMS or whether it's by someone banging a drum down the valley. Doesn't matter, as long as it's effective, it can work. So people then need to receive that warning, and they need to believe it. So trust is an element here. Whose information are you actually going to believe? And then you need to act on it. And as you can see from the Boxing Day tsunami, this gets pretty complicated because we're talking about operating over 11 different countries. This is a hazard that spread all around that vast area, and it changed over time. So we had the first main wave, we had the second devastating wave as well. And also, we've got to think about what is our early warning system for? Is it for the safety of people's lives, or is it for the safety of property? And what particular hazards are we interested in? So early warning systems are pretty complicated, and the United Nations have basically developed this early warning system structure that they have devised, which you can see here brings 4 parts together, which is risk knowledge, monitoring and warning service, dissemination and communication, and response capacity. So this is what they're saying are the 4 key components of an early warning system. And they call this a people-centered approach because they want the people who are vulnerable to be involved in that. It's not just something that's filtering down, top down. So now we come to sort of my questioning of, why was so many people killed on the Boxing Day tsunami? And actually, what I wanted to do, because I'd studied geology at an undergraduate level, was I wanted to go back to volcanoes. So I studied this question about early warning systems using volcanoes. And volcanoes are particularly interesting because they are actually one of the most complex natural phenomena that we have. And that's partly because it generates many different hazards. Of course, you may know of lahars, mud flows, lava flows, gases, hydrothermal activity. And of course, we can have all sorts of secondary hazards, such as tsunamis and flooding, and also ongoing stresses to the environment that can, in fact, create drought, disease, and all sorts of other toxic ramifications further down the line for those people living within that area. So what I did was I went to the United States and I worked with the United States Geological Survey. And I was interested in looking at how their observatories, which you can see a picture here, how they work, how do they get that information in it, and how do they then decide what's important and what's relevant. And you can see from this that essentially now it's all technically done. Everything's done remotely. This observatory is away from the volcano, which is a pretty smart idea in case it erupts. It's best not to have your observatory next to the volcano. And so I was basically working with these guys to see how they process this data. Now, one of the key things they do is they get this data in electronically, and then they have to make a decision about what that means. And the way they do that is using a volcano alert level. And a volcano alert level system is a bit like an early warning system. It's the way that the scientists convey what they think is going on to their various stakeholders, whether that's the public or other federal agencies such as emergency management, the National Weather Service, the Forest Service, the landowners, and so on. And you can see I've picked this one in particular because it kind of gets the point across quite succinctly that essentially what we're talking about here is the alert level reflects the state of the volcano. So at the top we've got the green happy volcano doing normal things, and at the bottom we get down to the red angry volcano that's about to blow its top. Little simplistic, but of course it conveys the message. Nowadays, the United States Geological Survey uses this alert level system, quite different, and it was one that was standardized across all of its 5 different volcano observatories. And you can see here, it follows actually more sort of weather terminology, like normal, advisory, watch, and warning. Now, one of the key issues with volcanoes, unlike tsunamis, where a tsunami event happens and then you have to respond to it, with a volcano, we're often anticipating what it's going to do. And the reason that we're anticipating that is because of this. Now this, if you're not already aware of, is a pyroclastic flow. It is the most deadliest hazard on the face of this planet. It travels around 450 miles an hour, so that's about the same as a jet engine. It's about 1,000 degrees Celsius, and if you get caught up in it, essentially you will not be able to breathe. It will go into your lungs, and it will also, so you'll be asphyxiated, and also you would then be burnt as well. So it's a really unpleasant thing, and obviously scientists are very keen to make sure that no one is within reach of the volcano, so that if it were to erupt, they would be affected by it. Now, what's interesting about pyroclastic flows is that they generally are produced by much bigger volcanic eruptions. And essentially what it is that plume of volcanic ash rising, and as it's got all this millions of tons of material rising, it needs a lot of convective heat to keep that material up. And eventually what happens is that it can no longer sustain that, and it collapses and it flows down the volcano. So these are pretty nasty, and this is a picture from Mount Pinatubo, which actually won one of the greatest photos of the century in National Geographic. And these guys actually survived because they were traveling this way and the flow was going that way. So they were pretty lucky, but you really do not want to get caught up in this. So when we're thinking about a natural hazard, we have to start thinking about what is the risk, because the event may not have happened yet. And so we start to bring together ideas of risk as a combination of the phenomenon, the hazard, and also the environment in which it happens. So the vulnerability of that population, the exposure or the resilience of that population to a natural hazard. Now, scientists actually tend to take a little bit more of a simplistic view, and they tend to feel that actually the scientists are really concerned with the hazard, and they're not concerned with the actual societal impacts of that hazard happening. That is the expertise of the local population, the emergency managers, and so on. And that's right, because those guys know which roads are going to be good to use or how to evacuate, and so on. Now, in the United States, the scientists in the Geological Survey have to make their decision purely based on the hazard. Okay? So bear that in mind, because I'm going to be telling you a little bit now about what I found. So, of course, my first key finding was that scientists find it really difficult to make sense of volcanoes. You've got lots of information coming in, lots of different types of information, and this is going to depend on how many types of technology and different methods you've got for keeping your eyes and ears on the volcano to see what's going on. So it's very difficult with all this data, and let's not forget that only around 10% of active volcanoes are actually monitored. So, we've got issues here that we might not be dealing with something that we've got data for, which makes it very, very difficult. Now, the other thing is that volcanoes behave very differently. So I've put up my favourite childhood game here, really because I wanted to read out this quote that one of the scientists told me. They say that when I try and describe this problem, I often use a medical analogy. There's a tremendous amount of information about the population of people, about the percentage of people that will have a heart attack, but when you come down to one person, you can't say, well, you're going to have a heart attack at the age of 63. We can say that 35% of the population will have a heart attack by the age of 63, but we can't say anything about the individual. And that's one of the really tricky things about volcanoes, is they kind of behave in different ways. And sometimes the triggers that they show to say that we're about to erupt is actually normal behaviour for a different volcano. It's pretty difficult. We then have the issue that, as I explained to you before, volcanoes have many different hazards. So we have here, for example, a diagram of gas. So in Hawaii, although the volcano is generally not disturbing many people, it might have a bit of lava eruption, the gas is going to really bother people who've got asthma or other respiratory illnesses that live nearby. So how do we communicate about those kind of hazards within this volcano alert level system? It starts to get really hard. And then, of course, we've got to factor in that there's going to be local institution requirements, local laws and procedures and protocols as to how this warning procedure should go. My second key finding was that actually scientists do not just base their decision on the hazard themselves. They do consider the risk. And often they don't realise they're doing it, but they are. And they certainly were in the United States Geological Survey. So here, I'll give you another quote here. Someone said that basically a change in the alert code is not necessarily purely volcanic. It is also political. Sometimes a volcano can be burping and not really affecting anybody, but in that respect, we may not change the alert level. At other times, when it is doing exactly the same thing, but a pilot saw it and reported it, we would have to do something about it. So the politics is driving it a little bit. So essentially what they're trying to do is take the context of the event and how that is going to impact on the ability for them to give a good, efficient warning. So, okay, we've learned that actually it's pretty difficult to get the scientific information. We've got a lot of uncertainties involved, but then we need to communicate that. How do we communicate that? Well, there's one little lesson we can learn here, which is actually from Nevada de Ruiz, which is a volcano in Colombia. And in 1985, this volcano was showing signs of unrest, and the scientists came in, and what they did was they created a hazard map. And this hazard map is essentially showing that what could happen is that when the volcano erupts, it would melt the ice on the top of the volcano, and it would create a mud flow like a lahar. And this lahar has, over the last few hundreds and thousands of years, typically flowed down to Armero, which is roughly around 60 kilometers away. Now, the scientists saw this unrest, they produced this map and took it to the local authorities and said, look, we think this volcano is going to erupt and it's going to create a mud flow. You need to be prepared, educate your populations about what's going on. But what happened was that the mayor and the priests said, well, this is too alarmist, this is too extreme. Can you go and redraw the map? Unfortunately, a few days later, the volcano actually erupted, and we got, unsurprisingly, a lahar that came down and killed over 23,000 people. Now, this wasn't a very big volcanic eruption. It was actually very small. But we can learn some really good lessons here. Yes, the scientists didn't have great certainty about when the volcano was going to erupt, but they knew enough to be able to engage with the local populations. But they did not want to pay attention to what was going on. They didn't want to invest any money in being prepared for a potential lahar. They didn't want to pass that information on to their populace because they thought that scientists were being scaremongers. So very, very difficult situation, and it obviously had tragic, very tragic ramifications. So if we bring this back to my USGS example, what we're looking at here is the USGS in this kind of complicated diagram here is having to communicate with lots of different people. It's having to communicate with the public, landowners, the media in particular, and how you manage the media, but also all the different federal departments that depend on that information so that they can make decisions about their own interests. So it gets pretty difficult. And then we have the question of, when do people actually communicate that information? At what point does the scientists feel confident enough that they can give that information across to people to take action? And so here we have an issue where actually a lot of the user groups that I interviewed, like the National Weather Service, were saying things like, actually, you guys spend so long focused on how to word exactly the statement that's going to tell us the information. And actually, all we want you to do is just pick up the phone and tell us that something's going on. We understand that there's uncertainty. So there's a bit of a disconnect here between, the timing of information and the desire to make things certain. And certainly, it's also a question of making sure that someone understands what you're saying. I am talking to you now, and I think I'm conveying a certain message to you, but you may be interpreting that in a slightly different way, based on perhaps your education system or the cultural background that you have. So how do we then know that people are receiving the exact message that we want? And it gets pretty difficult. So, because we're in Britain, I thought I'd throw something in about the weather, because we love to talk about the weather. So here we have a 30% chance of rain. What does that mean? So, for some people, it meant that 30% of the day it was going to rain. Some people thought it meant that 30% of a region will receive rain. And this diagram here said that people thought that out of 10 meteorologists, 3 out of that 10 thought it's going to rain. Now, this is perfectly logical, but what does it mean? What it really means is that on any given day that you have a 30% chance of rainfall, it is that chance that it's going to happen that day, 30% chance that there will be rain on that day. And so this raises questions as to how experts can actually convey information in a way that people can understand. And this brings us to all sorts of questions about what does probabilities mean, what does risk mean, and certainly here, there's all sorts of work that actually says that we're not talking about risk, we're actually talking about uncertainty, because we can't quantify things, we can only give a qualitative estimate about these things. Now what this leads me to is really the L'Aquila event, I should say. So here, you may remember in 2009, a pretty significant earthquake happened and killed a couple of hundred folk. And this caused an outcry, partly because the media portrayed it that scientists had been blamed for not forecasting the earthquake. But actually what it was a miscommunication of what was going on. And you can see here what happened was that the emergency managers, the civil protection and the scientists were working together, and they basically established that yes, it's likely we're going to get earthquakes, we're in an earthquake region, but you know, the probability of us getting a large earthquake is pretty minimal. And that was their downfall, because they couldn't say that the probability of an earthquake not happening any more than they could it happening, because we just don't know with an earthquake. At this point in time, we don't have any warning systems other than potentially 30 to 50 seconds in some countries. So obviously the people who had normally taken their course of action with their family and slept, say, outside or gone and visited family, didn't do that because they felt reassured. And that's really what this crisis was all about. But more than this whole trial of taking the 6 scientists and the 1 civil protection employee to jail, essentially they were then given a jail sentence, and this was then revoked a few years later, and actually now there's only civil protection chap who needs to go to jail. So here we have go straight to jail. But what really concerned me was that when I was at conferences in various places around the world, I was suddenly seeing disaster specialists, volcanologists, tsunami specialists saying, I don't want to give my opinion, I don't want to end up in jail, I'm really worried about, you know, what do I do? How can I communicate what's going on? Because I'm worried that I'll get into a litigation process. And so my research on the one hand in the United States was saying, we need to be open, we need to be transparent, we need to engage with everyone. And then this event comes along and says, no, you've got to be careful what you say, because if you say something, you could end up in jail. So this brings me on to my final question of, well, who is accountable then? Who's responsible when we're looking at these events? And you may, of course, remember the volcanic eruption of Eyjafjallajökull. And I've been told that I've got to try and at least get you to pronounce it, but it is, as I understand it, Eyjafjallajökull. And it erupted in 2010, and as you may remember, caused chaos. Airspace was closed for over 6 days. It was the longest time airspace had been closed since the Second World War. And of course, the airline industry and Europe was pretty much being captured by this ash cloud. Now, why was that? Why were planes not able to fly during this volcanic eruption? Well, in 1982, a British Airways flight was flying over Mount Gunung in Indonesia. And the passengers started to see something funny happening around the plane, sort of weird smells and fires and so on. And then they got, you know, the ding-dong that comes on and it says, ladies and gentlemen, this is your captain speaking, we have a small problem. All 4 engines have stopped. We are doing our damnedest to get them under control. I trust you are not in too much distress. Don't know about you, I would be quite concerned at this point. But to the credit of the captain, he did keep everyone pretty calm, and he managed to turn the plane around, thinking I wasn't in this problem before, so he turned the plane around, it glided down, and then it was able to actually get some of the engines working and land safely. And when they opened up the engines, this is what they saw. This is actually a photo by Sir Eric Moody, who was that captain. And you can see here that it's basically a choked engine. What's happened is the volcanic ash, which is essentially tiny bits of glass, have been sucked into the turbine here. They get heated up, and then it sticks to the engine, and it chokes it, and the air can't get through, and it fails. So clearly, the whole aviation sector was, wow, we need to do something about this. We cannot let planes fly in ash because we don't want to risk lives, and also damaging engines is going to be really expensive, okay, because jet engines are very expensive. So they set up this whole warning network between observatories, the Met Office, scientists, pilots, because pilots are quite often the first person that can see a volcano erupting. And they basically said, if we have ash, we're not going to fly. Now, what happened in Europe was this then was challenged deeply. This idea that if there's no ash, we can't fly. And this is because Europe was a very different context to how volcanic ash had impacted other countries around the world. If we think of places like America, South America, New Zealand, those places, there's a very strong trade wind normally that will take the ash in a certain direction, and you can fly around it. You can get to another part of the country easily. But in this case, we had an ash cloud that was sat right over Europe. This is an area where people are commuting to work, doing business every day, lots and lots of flight paths. It was one of the most busiest flight paths in the world on a daily basis. And of course, people couldn't even get in and out of their country because they had the ash cloud, so they couldn't get around the problem. And on top of that, you had countries in Europe going, we don't even have volcanoes. Why are we being affected by a volcano? This is madness. So the Met Office here in the UK did a lot of work to try and understand where the ash is, how high it is, and where it's going. And they produced these maps, which you may remember seeing on the news, about where the ash is thought to be. So I'm guessing you're saying to me, well, thinking isn't good enough. Why are we modelling it? Why don't we know where the ash is? And there is actually a way we can know where the ash is, and this is using LiDAR, radar technology, which will sit on the ground and it will send a beam upwards, and when it hits a cloud or an ash cloud, it will basically bounce it back, and you'll be able to get a picture of what's going on. And here you can see such an image showing some low clouds here and then some volcanic ash. Now, if we had these all across the country, working on a real-time basis, we could know exactly where the ash is and how high it is and fly around it. But we don't, because it's really expensive. So ultimately, what we ended up was in a situation where everyone was pretty much in the dark. The scientists didn't know really where the ash was and how high it was and what its concentration was. And the engineers didn't know how much ash is needed to cause an engine to fail. And this is partly because, you know, they don't want to test engines by putting loads of ash in it because it's expensive. Very, very sensible. So we ended up with this situation where there's a lot of uncertainties, there's a lot of risks involved. What happened? Well, essentially, that whole standardized procedure was thrown into the bin, and eventually new safe limits were established of saying, well, we can fly through 2 micrograms worth of ash. Now, this number, not really sure where it came from, because after 30 years of air travel being affected by ash, it seems a little bit weird that in 3 weeks they managed to suddenly find a definition. But, okay, they did that. And then, of course, they started to think, well, we need to remove the buffer zone around it. We had a buffer just in case, but we don't need that now. And in fact, they ended up saying, it's okay, you can fly through a little bit of ash. But is it? So, are we really being risk savvy? And what is going on here? Whose risk counts? Is it the risk of the airline industry who are losing money? Or is it the risk of potentially a passenger on a plane being killed by the plane coming down or damage to an engine that may happen subsequently? So we can see in this case, the scientists were pretty powerless, the engineers were pretty powerless, and actually it was business and policy that was driving the need to get the country moving again so that we could get supplies in, get people travelling, and so on. So here we have a very different situation of asking who's important, what's our priority. So to conclude, what I really want to do is say, okay, well, what can we take from everything that I've said today? How can we be risk savvy? Well, you may remember the initial UN diagram that I brought up of early warning systems. And you can see what I've done here with my co-author, Carolina Garcia, is what we've said that it's not these parts of an early warning system that fail. It's the things that link them that fail. It's things like increasing participation with the local communities, defining accountability so that people know what the legal rights or not are when they're trying to give information. It's about risk education and continuous communication. So really, what I'm saying here in terms of lessons learned is that effective early warning systems do really work. And they can really communicate very effectively very complex situations. But there are always going to be inherent uncertainties, but that doesn't mean that warning system won't work. I've also shown that local contingency is very important as to how that risk may be understood. And also establishing key roles and responsibilities, which was the big issue in L'Aquila. We've also got to be careful because the UN is saying we need to have more standardized, globalized early warning systems. And I hope what I've told you today is actually that can be quite dangerous because it needs to be relevant for the area that system's working, which makes it difficult. And of course, education and who's making the decisions is very important too. So finally, what I'm saying is that ultimately, as long as everyone's communicating with one another, there are ways around these complexities. And what I'd like to do is leave you with this final quote, which I think really sums it up, which is essentially that reorganizing the social role of scientific uncertainty will help us to see how many of our problems about risk are deeply cultural and cannot be overcome simply by the application of more and better science. So thank you very much for your patience, and do let me know if you've got any questions.
Thank you, Carina, for a really thought-provoking talk. That's excellent. Thank you. So we'll take questions from the audience, and I also need to keep alert to Emma, who's been receiving questions in from outside. And so, gentleman here had the first one, I think. Okay.
Thank you, that was great. Now, you've shown us that people get sent to jail for missing disasters, and you've shown us that commercial influences can perhaps adjust the tone of the communication that's given after there's been some sort of disaster. Can I just ask about everyone's favourite person? That's the health and safety officer and the safety culture. Have you any idea how much money has been cost and lost and wasted as a result of overcaution by overzealous people calling foul too early and causing everyone to go into fear and meltdown mode that didn't really result in a disaster at all?
Great question. So in terms of disasters, generally, most money and attention is actually paid to post the event. So actually only, I think, about $1 to $3 is actually spent out of $10 in preventative actions. But the amount of money that's invested gives a huge return after the event. So it begs the question as to why actually we're not doing more beforehand, because actually it's shown to be economically advantageous. So it's a tricky balance that we've got here. And the other problem is, as you raised rightly, is if we create too much concern and worry, will people pay attention? I mean, how many of you guys, when you hear the fire drill go off, go, oh no, I'm just going to wait a couple of minutes and see if it's a test or it's an error, and then eventually you'll get your bag together and think, oh, okay, well, maybe I'll get a coffee or something. It's that complacency, but essentially what's important, studies have shown that as long as you explain to the populations and the people affected why there was an error, they then are able to understand and take that on board and actually respond effectively next time. So it's a tricky balance, but I would perhaps argue that more needs to be spent on prevention and preparedness, actually, than trying to stick a plaster over things in the end.
I'm going to take one more here. I think the gentleman here had a question. No? Oh, here we go. Sorry. Okay, so one more from the room, and then I'll go to our external.
Bear in mind our last tsunami was in 1607. Do we need an early warning system off whales?
It's a very good question, and actually it's even thought that the Lisbon earthquake, which I believe was in 1755, created a tsunami which would affect the UK. The UK is vulnerable to tsunamis, absolutely. This can be from earthquakes that happen, say in like Lisbon, or it can be from giant landslides that happen, particularly the Storegga slide towards Norway. Lots of unstable sediments there that can slope and fall down and create a tsunami. So yes, there is an argument that we should have a tsunami warning system. But what's interesting is that following the Boxing Day tsunami and the Japanese tsunami Tohoku in 2011, many different regions in the world are now talking about bringing in early warning systems. So the Caribbean, the Mediterranean, and so on are developing these systems. So maybe it won't be too long before we do have some form of system here in the UK.
So I believe that there are questions that are coming in from external listeners.
Yes. So via slido.com, 2679 for those playing at home. One of the questions sort of talks about disaster movies that we've all seen, and the scientist is like running into the room and shouts at everyone to pay attention, and they're sort of ignored. And the question is kind of around the legality of what you were saying about the scientists sort of not wanting to say anything. Would you recommend there's a sort of unilateral legal exemption that should be applied for scientists in these scenarios?
So it depends which country you're operating as to what your legal rules and regulations are. So for example, in the United States, in the Geological Survey there, the person who gives the information is not responsible. They are a federal agency, they're part of the government, and if you wanted to have any kind of argument about that, you would have to have that with the American government, which obviously makes it a very difficult and expensive case to do. But equally, what they're really good at, in the US in particular, is that they bring together lots of people's different opinions and they make sure that they're all singing from the same hymn sheet. So they're giving the same information out. There are other countries, clearly, where the responsibility to make decisions based on not just the hazard, but the risk as well. And there are other countries where the volcanologist, if you like, has to make decisions about evacuation as well. And that complicates things and it can present problems. So it really depends on the legal context. But ultimately, a scientist is always teetering on that balance between trying to give people ample time to adjust to the potential that something may happen versus actually scaring people and causing problems. And it's a really hard line to draw.
Do we have another question from the room? Yes, we have a lady here.
Thank you. So I think you know where I'm coming from because we're colleagues. But it seems to me that a good part of your story is also about the public. And it also seems to me that for you, the public is not this kind of uniform mass, but it's quite diversified. And each one of the cases that you've looked at obviously entails a different response from the public. So can you maybe tell us a little bit more about the work that you've done to understand how the public receives early warnings and maybe connected to the idea of risk education, because I think that goes quite hand in hand.
Absolutely, and a really good example I could perhaps give is things to do with tsunami early warning systems. So obviously on one hand we have a very expensive technical system that will detect an earthquake and be able to detect if there's tsunami waves generated. But actually a much cheaper and more effective way of doing it is actually scientists designing educational programs for schools to teach, or scientists going talking at schools or public lectures like this, to actually say, you know what, if you feel an earthquake and you hear some weird sounds like a train and you can see the water being pulled out, that's a tsunami and you need to get to high ground. It's as simple as that. That's an absolute simple case. In the case of L'Aquila, it's about building earthquake-proof buildings. But this is hard for Italy because they've got very historic, beautiful buildings, some of them which are being protected by World Heritage sites. So it's very difficult to actually get things to change in some senses, certainly with building codes, it requires a lot of investment, but actually education can be really, really cheap and useful. So when we're trying to engage with the public, it is about thinking about who are the public? They're not just this blob out there. They're actually people who are smart people thinking, and often they know much more about the hazard and what to do in response than the scientific experts. So really, it's all about all those experts coming together, communicating to come up with the best solution that's going to work given the uncertainties and the constraints of that scenario.
Okay. I think that we must close there because we must vacate the room for another class that's coming in. I do know that there are many more questions that have come in online, and I think that Emma will be transmitting those to Dr. Fearnley. I think that she's also agreed to make herself available to answer further questions that you might have. And with that, we'd like to thank you for attending today. Could we please ask you to fill in your appreciation forms about the lecture today and about the series in general, and we'll see you back here on Tuesday. Thank you very much. Bye.